my name is Hanwen. I'm from University of Oxford, and the title of our paper is Distortion Estimates for Approximate Bayesian Inference. When we perform Bayesian inference, approximation is often inevitable. After we got an approximate posterior, we want to know if the approximation is any good. In this paper, we propose a new diagnostic tool. We will focus on the univariate marginals of the approximation and give a visual diagnostic which reflects how the true marginal posterior is distorted by the approximate without recovering the truth. We first introduce a distortion map, which is a function that acts on the univariate marginal CDF of the approximate posterior at a generic data point y. Let Fy and Gy be the marginal CDF of the true and approximate posterior conditioned on y. We define the distortion map dy by this equation. This means for any parameter value x, the distortion map will bring the approximate probability to the exact. By differentiating both sides with respect to x, we also have this equation on the density level, where the lowercase dy is the derivative of dy. From these two equations, we can see that one approximation is perfect if and only if dy is the identity map, where lowercase dy is constant 1. This means we can plot dy as a visual diagnostic by comparing it to the identity map. One thing we would like to stress is that it seems like if we could estimate dy, then we can essentially recover the true marginal. But our goal is not to recover the truth, but is to see if the approximate is substantially different from the truth. In this paper, we show that asymptotically, dy will bring the approximate closer to the truth with high probability. One nice property of dy is that dy itself is also a CDF. We can easily verify that dy is monotonically increasing and is bounded between 0 and 1. In addition, if we have x coming from the true posterior given y, then the approximate marginal CDF g of y evaluated at x must be a sample from the distribution specified by the CDF D of y. Therefore, we can say that G of y is a perfect approximation if and only if gy of x follows a uniform 0-1 distribution. We parameterize lowercase dy, the derivative of dy, by a beta density. This means dy is a beta CDF, where the parameter a and b are outputs of a neural net with weight w and input y. The weight w can be learned by maximizing the log likelihood of q given y, and our goal is to estimate the distortion map at the observed data y-obs. Here is how we do it. We only need the observed data y-obs, an approximation scheme which takes data vector y as input and returns the approximate marginal CDF. And we also need functions to sample from the prior and the observation model. We first sample pairs of parameters and data from the generative process. Then for each yi, we apply the approximation scheme, get the approximate CDF g of yi, and evaluate at xi. From last slide, we know that for each simulated data yi, this quantity is a sample from the distribution specified by the CDF D of yi. And then we fit a neural net with input yi by maximizing the log likelihood of qi. Recall that each of these lowercase dy are beta densities. Once we have fitted the model, we can plug y-obs in, get the estimated distortion map at y-obs, and compare it to the identity. Comparing two existing methods such as Tolls et al. And Prangos et al., our setup allows us to diagnose the approximate posterior specifically at y-obs. In contrast, the existing method only focuses on the averaged performance of an approximation over the data space. This could be misleading, as we will show in our example, because one approximation can be good on average, but poor at the observed data, or the opposite. But our approach could avoid that as we directly target y-obs. In the paper, we also extend our approach to bivariate cases, which allows us to diagnose the dependency between parameters. We then apply our approach to a social network model. We fit the karate network data to a 3-parameter exponential random graph model. Then we check the performance of different approximation schemes. Here we present 2 approximations. The top is a regression-adjusted ABC posterior of the first parameter of the model. The bottom is the variational approximation of the same parameter. We plot the exact and approximate density on the left. We can see from top left that the regression-adjusted ABC posterior is overdispersed, while from bottom left, we can see the variational approximation is underdispersed. On the right, we plot the exact and estimated distortion map at y-obs in black and red curves. We can see they agree with each other and deviate from the identity map in both cases, which means they successfully identify the approximation error. In addition, we also plot the averaged distortion map over a subset of data space centered at y-obs in green. For variational approximation at bottom right, the red and green curves agree with each other. This is when our approach agrees with the existing methods. But for the regression-adjusted ABC on top right, we can see the green curve is quite close to the identity. This is when the approximation works well on average, but poorly at the observed data. In this case, the existing methods will give misleading diagnostic results because they are based on the averaged performance, while our approach could correctly capture the approximation error. To conclude, we propose a new visual diagnostic tool for marginal approximate posteriors. Our methods check the performance of approximation specifically at the observed data y-obs, not averaged over the dataspace. The distortion map d of y attempts to move the approximate closer to the truth, but do not try to recover it. And we also applied our approach on a doubly intractable social network model. That's it. Thank you for your time.